Graphs of some trigonometric functions. First off, the graph of sine of x. Start off with a table of values. These points should be familiar to you. The graph itself should be familiar. All that's changed is rather than working in degrees, we're working in radians. Sine of 0 is 0, of pi over 2 or 90 degrees is 1, of pi or 180 degrees is 0, and so on. We call those the 5 key points of the sine graph. If you know these 5 points, they'll be useful in the long run once we get to transformations. Sine graph starts at 0, 0, heads up toward its maximum, back down to 0, -1, and ends off at 0. We say that this is one full cycle of the sine graph. Now, of course, we say that the sine graph is periodic and keeps repeating itself. Every 2 pi, it'll be at the exact same spot. We'll have another maximum 2 pi later. We'll have another minimum 2 pi later, and so on. The domain of the sine graph is all real numbers. You can take sine of any number you'd like. The range, on the other hand, is between -1 and 1. When I take sine of a number, the value is always between -1 or equal to -1. The value is always greater than -1 or less than 1. You can see from the graph that there's a maximum of 1, a minimum of -1. Recall that the amplitude of a graph is how tall each wave is. The amplitude is always positive. It's the height of each wave. We don't say that this height is -1. It's a height of 1 here or here. The period is 2 pi or 360 degrees. And lastly, the axis, that's simply the line that sort of cuts it through the middle. It sort of rotates about that line. It goes 1 above the line, 1 below the line, and so on. The graph of cos x looks almost the same as the graph of sine x. In fact, it's just the graph of sine x shifted pi over 2 to the left. It's also got 5 key points that are good to remember. And it's got all the same properties. What differentiates the two graphs is that cosine starts up here at its maximum and ends way over here at its maximum, and then it starts repeating again, whereas sine started at 0 and ended at 0. And now the graph of tan x. You may remember tan of x is defined as sine of x divided by cosine of x. That's an identity we'll come back to later. Here I've summarized what we just found out about sine x and cos x. They're 5 key points. So using this definition, tan of x equals sine x over cos x, we can generate a few key points for tan of x. When x is equal to 0, if I divide sine of x by cos of x, I get 0, 0 divided by 1. But at pi over 2, sine of x is 1, while cos of x is 0. Now if you recall, if I try dividing that 1 by 0, we can't have 0 in the denominator, and for that reason, we say that tan of x is undefined at that value. And what happens is we actually get a vertical asymptote on the graph. Doing the same thing here, sine of x is 0, cos of x is -1, dividing results in 0. And again, because cos of x is 0 here, at 3 pi over 2, it's undefined again. So you notice every pi, you end up with a 0. And beginning at pi over 2, every pi, you'll get a vertical asymptote. The end result is this kind of bizarre looking graph over here. At pi over 2 and every pi units after that, I've got a vertical asymptote. And at 0 and every pi after that, I've got a 0. And the graph of tan is always increasing. And then we have to approach the asymptotes here. It goes toward positive infinity that way, negative infinity that way, positive infinity, negative infinity, and so on. And now the graphs of the reciprocal trigonometric functions. You should remember that the definition of cosecant x is the reciprocal of sine of x, or 1 over sine of x. So once again, if we know the 5 key points on sine of x, we can generate the points on this graph. So first off, the reciprocal of 0, or 1 over 0, is undefined. We can't have 0 in the denominator. The reciprocal of 1, or 1 over 1, is 1. Once again, the reciprocal of 0 is undefined. The reciprocal of -1, 1 divided by -1, is -1. And once again, reciprocal of 0 is undefined. That means we've got vertical asymptotes here, here, and here. Everywhere the graph of sine of x has zeros, the graph of cosine of x is going to have vertical asymptotes. Now plotting the other 2 nice points, pi over 2, 1, and 3 pi over 2, -1, there and there, we can piece together what the rest of the graph looks like. We know that it has to approach the asymptotes. That's the definition of an asymptote. So it's going to have to go up toward infinity there and up toward infinity there, and once again approaches the asymptote but never touches or crosses it, Same thing happens in here. We're down in the negatives. This is going to approach negative infinity that way and negative infinity that way. The graph of secant of x looks very similar. Makes sense, the graph of cosine is a shift of sine. The graph of secant is simply a shift of cosecant. Making a table of values, we generate our key points once again. The reciprocal of 1 is 1. The reciprocal of 0, undefined. The reciprocal of -1 is -1. Reciprocal of 0, undefined, and so on. Everywhere the graph of cosine has zeros, the graph of secant has vertical asymptotes. Where cosine equals to 1, secant also equals to 1. Where cosine equals to -1, secant also equals to -1. Putting it all together, we get a graph that looks similar to the cosecant graph. We get a graph that looks similar to the cosecant graph. These sort of U shapes in each of these little sections. And finally, the cotangent graph. Cotangent can be defined as cosine of x over sine of x. Using that definition, we generate these points. Alternately, you can take a look at the tan graph and the key points on the tan graph and take the reciprocal of those. What you'll find is everywhere the tangent graph had zeros, the cotangent graph has vertical asymptotes. Everywhere the tangent graph has vertical asymptotes, the cotangent graph gets zeros. Remember that the tangent graph increases everywhere, while the cotangent graph decreases everywhere and approaches the asymptotes up toward infinity and down toward negative infinity. Now we're going to take the base functions, sine x and cosine x, and apply the same transformations that we've applied to other graphs to these. These should look familiar. Your a value is the vertical stretch, and it also lets you know if your graph's been reflected. If your a is negative, it's been reflected across the x-axis. But for a sine graph and a cosine graph, it gives us a special property. We say that the absolute value of a, the positive value of a, is the amplitude of our graph. Remember, that's the height of each wave. Remember, the k value lets us know if our graph has been horizontally stretched or compressed by a factor of 1 over k, always the reciprocal. The k value also gives us an important feature of our graph. It'll tell you the period. Remember that for the base function sine x and cosine x, the period is 2 pi. If there's some k value, the period is going to be stretched or compressed by that value of k. So we take the period 2 pi and divide it by whatever your k value is. We can also find our k value given the period by taking 2 pi divided by whatever the period of our new graph is. The d value, remember, is simply a horizontal translation side to side in the opposite direction than we expect, minus to the right, plus to the left. We give it a special name for sine graph and cosine graphs. We call it the phase shift, just a special name. Finally, the c value is your vertical translation, up and down, no different, but it also gives us an important feature of a sine graph or cosine graph. It lets us know the horizontal axis, or the middle of our graph, how high our waves are going to go from the center. I've graphed an example here. Looking at this equation, I've taken the base sine graph, reflected it across the x-axis, vertically stretched it by a factor of 2, horizontally stretched it by a factor of 2, shifted it pi over 4 units to the right, and finally shifted it 1 unit up. So as a result, these are the properties of this graph. It has an amplitude of 2, your positive a value. It has its middle or horizontal axis at y equals to 1. The period has been doubled. Once again, take your k, take the reciprocal, find your period. And lastly, it's been shifted pi over 4 to the right. To make a good sine graph or good cosine graph, you need 5 key points. You take the 5 key points from the base graphs, 0, pi over 2, pi, 3 pi over 2, 2 pi, and transform them to 5 new key points on the new graph. You'll notice my graph now has its middle or horizontal axis at 1. It has an amplitude of 2, 2 down and 2 up. It has a period, 4 pi units. The entire thing was shifted pi over 4 to the right. You'll also notice it's been flipped. Usually the sine graph heads up toward the maximum, down toward the minimum. This one goes the other way around, heads down toward the minimum and then up toward the maximum. Periodic motion can be modeled with sine graphs and cosine graphs or sinusoidal graphs. So things such as pendulum swinging, something rotating in a circular motion, springs bouncing, that's examples of periodic motion. So I've given an example here of riding a Ferris wheel. So I've sketched a Ferris wheel with a diameter of 26 meters from here to here, and you get on 1 meter above the ground. Of course, we don't want it scraping on the ground. Let's say it takes 1 revolution to complete a full cycle on this Ferris wheel. We want to know, if a rider gets on here 1 meter above the ground at 0 seconds, find an equation that models the rider's height as a function of time. How high are they 10 seconds later, 20 seconds later, etc. So I've organized all my information here. You may find it useful to draw a graph. Not necessary, but useful. So here's where my rider gets on at a height of 1 meter. There's my rider's maximum height, 27 meters. If a rider gets on at a height of 1 meter and the diameter of the Ferris wheel is 26 meters, they're going to reach a maximum height of 27. And we said that a full revolution takes 60 seconds to complete. Rider gets on, reaches a maximum 30 seconds later, completes 1 full revolution in 60 seconds. So I've calculated the important values I need to find here. A, or my amplitude, is given by the maximum minus the minimum divided by 2. My maximum value is 27, my minimum value is 1. We find that your amplitude is 13. To find the k value, we use this property. K is equal to 2 pi divided by the period of your function. We said that it takes 60 seconds to complete 1 full revolution. So k is equal to 2 pi divided by 60, and simplifying, k is equal to pi over 30. To find c, or the middle of our graph, the axis, we take the maximum value plus the minimum value divided by 2. Simplifying that, it's 14. And lastly, do we need a phase shift? Well, that depends. If you choose a cosine graph, remember that the cosine graph begins at a maximum and ends at a maximum. We do not need a phase shift because this graph begins at a minimum and ends at a minimum. So if we simply flip it and use a negative a value, we can take care of that. If you decided to use a sine function for this, we would have to start way over here where it has been shifted. Much smarter to use cosine. So putting this all together, I get that equation. The height of the rider is given by negative 13 cosine pi over 30 t plus 14.